Here we are in section 5.5 with numbers 19 through 24. It says to factor the following completely all the way down, and if it's not factorable, label as prime. Now, it doesn't give us specific instructions, so we're going to keep all of the options open, 1, 2, 3, 4, 5, and let's not forget, don't jump the gun, get that greatest common factor out first if we can. Okay, here we have x to the 8th minus 81. Any greatest common factor? No way. This has all x's, that's all made up of 9s, 3s, stuff like that. So, how many terms does it have? 2, so we're not going to use method 2, method 3, or method 4. This is a special case, particularly with a difference of squares. That's the main one we're focusing on for the special cases. And this is a difference, indeed. So this is going to break up into x to the 4th plus 9, x to the 4th minus 9. Good. Oh, look at this. We have two binomials. This one is now a sum of perfect squares. Can't go down anymore. But this one is a difference of squares again. So I'm going to kind of box this guy so we can see what that comes out to be. This is a difference of x squared squared and 3 squared. So this is going to break up into x squared minus 3 and x squared plus 3. Indeed. Ooh, now these are each binomials. That one's got a sum, so we can't do anything in there. But this is a difference of, oh, x squared. Nope. 3 is not a perfect square. So this is our complete answer here. There we go. Good. Okay, number 20. Ooh, this is going to be a special case if we get to there. But first, don't forget, greatest common factor. Can we pull anything out of a 12 and a 27? It looks like a 3 will come out of there. We could pull, there's an x in both of them. There's a y in both of them. And we're left with 4x squared minus 9y squared. Now let's check that and see if he actually breaks up. Difference of squares, and indeed 4x squared is a perfect 2x and 2x. And 9y squared is a 3y and a 3y. And we make sure that we have a plus here and a minus there, and that'll make sure it works. So let's bring this guy down, and this is our complete factorization. There we go. Number 21. First step, pull out a greatest common factor. Oh, there's nothing there. X squared minus 3x minus 18. We have 1, 2, 3 terms. So we are down here at item 3 or 4, and we notice leading coefficient, ta-da, is 1. And so that's method 3, which is just put these in, put the x there, put the x there, and we just have to look at this last number, negative 18, and see what times is to 18 and adds to a negative 3. 1 and 18, 2 and 9, 3 and 6. Those are the 3 options that multiply to 18. And let me see, what do we have there? Negative 6 and a plus 3, will that do it? It looks like that will. That'll add to the negative 3. So plus 3 and minus 6. And we're good. Next one, number 22. Any greatest common factor in this? No. So we count the number of terms. 1, 2. Well, we're not method 2, 3, or 4, so we're looking to see a difference of squares. Hey, look, that's a difference right there. So we're going to have y to the 4th, y to the 4th, and then this is going to be a k to the 6th, k to the 6th. And one's a plus, and one's a minus. Now, we have two binomials right here. This one still has a minus sign, and look, we can break it down even more. Y squared minus k to the 3rd, and y squared plus k to the 3rd. And we'll bring this guy down, y to the 4th plus k to the 6th. Now this guy can't factor anymore because there's a plus sign in the middle, and sum of squares doesn't work. It is a difference of squares. That means a minus sign. This guy looks like it almost could go down again. Y squared minus, but no, k cubed. That is not a perfect square, so it looks like we are now complete. Okay, number 23. Ooh, look at that one. 16a squared plus 40a plus 25. Is there anything we can pull out with the greatest common factor? 4 can come out of 16 and 40, but there's no 4 in 25. It's only got 5s in it, and there are no 5s in 16. So nope, greatest common factor is shot. We count the number of terms. 1, 2, 3 terms. And it looks like we have a leading coefficient right here. That's not 1. It's 16. So we would have to do 16 times 25. Now, there is a special case using the squares. Let's just check and see if it's a perfect squared trinomial. So that means we do this guy squared. Look, 16 is a perfect square and 25 is a perfect square. So let's just take a shot in the dark, stab it out, and see if 4a plus 5 altogether squared, see if it works. Certainly 4a times 4a gives you 16a squared, and 5 times 5 gets you 25, but the middle term would be 4a times 5 times 2, because there'd be two middle terms there, each of a 20a. Yes, it works. So that just saved us a lot of work. 16 times 25 would have been like 1600. We would have had to factor it clear down, or 400, sorry, and we would have factored all the way down to 20 times 20. All right, let's try this one. Z to the fourth plus 8z squared plus 16. No greatest common factor. Has 3 terms. Leading coefficient 1. So z squared is going to go there. Now we have to find two numbers that times to 16 and add to 8. And it looks like it is a 4. And can these be broken down at all? No, they're sums of squares. If this were a minus in here, either one of them, we could then break it down to z plus 2, z minus 2. But there we have it.